Welcome to the tutorial of the first lesson about binary data. You got an exercise sheet with some information and tasks which you should solve, and today I want to give you solutions so that you can check if everything was correct what you did. So in the back here you see the exercise sheet. And we directly want to start with the first question. How many bytes are needed or required to represent the decimal number 1024? So we do the same stuff what we always do if we calculate in binary. So we write the representation. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. So this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we want to represent 1024, binary, it's this. And then how many bytes are needed for that? You just count. One byte has 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So you have 1 byte and you need another byte. So you need 2 bytes to represent this number. So this is task 1. Let's come to the second task. The second task is which decimal number is given by the binary representation 11010011. And we should show the calculation. Again, quite simple. We have the representation 1101 0011, and then we write the decimal values for the individual position. So this is 1, 2, 4, 8, 16, 32, 64, and 128. And then we sum up all of this. And what we get is 211. So the binary representation here is 211 in decimal. 2. Let's go to question number 3. Convert 11101100110001 in binary to an octal number. This is the base 8. So now you have different possibilities. You can of course convert the binary number to a decimal number and then divide always by 8 so that you end up with an octal number, or you use one trick that you have between 2 and 8 and 16, you have a relation by a division factor. And therefore, you can do the following. So we write the value. So 1, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1. So, and if we want to convert it to octal, we make groups of 3 bits. Therefore, I already arranged it like that. So we make groups of 3 bits and convert it to the corresponding decimal number. So in this case, we have 1 plus 4. So 1, 2, 4. 1 plus 4 is 5. Here we have 4. Here we have 5. Here we have 2 plus 4, which is 6. The same here, 6. And we have 1. And this is already the resulting octal number. Let's continue with question number 4. Convert number from question 3, so the number we already had, to a hexadecimal number. So if you remember what we did, we just grouped here. So therefore, we can use the same trick. So what we do is, we now group 4 bits to one new value. So here, 4, here, here, and here. So that we have a new combination, and then we can just convert this again to the decimal number. So in this case, it's 5. Then we have 2 plus 4, which is 6. And then we have here 1 plus 4 plus 8. So 1 plus 4 is 5, plus 8 is 13. So we have 13. And 13 is, 10 is A, 11 is B, 12 is C, 13 is D in hexadecimal. And then we have 2 plus 4 plus 8, which is 14. And 14 is E in hexadecimal. So, therefore, we have the hex representation. And this is question 3 and question 4. So let's continue with question number 5. Convert the decimal number 2123 to a hexadecimal number. You have again now 2 possibilities. So the first one is you divide by 16. It's the same what you did with binary, so you divide by 2. Here you divide by 16. So let's do this. We have the number 2, 1, 2, 3. And then we divide it by 16. So let's do that. Divide by 16. Result 132, and it's an integer division. So therefore, what we get is a rest, which is 11. 11 is B. Then we take this 132 divide by 16 and we get 8 and rest 4. Then we take this 8, we divide it by 16, it's 0, rest 8. And then we read it from this direction, so the result is 8, 4, B. We can of course do also another solution for that. So if we have this, we can convert to binary, and then we use this trick here to convert to the hexadecimal version. So what we do is we take 2123 and divide by 2, which is 1061, and the rest 1. 1061 divided by 2 is 530, rest 1. And then 530 divided by 2 is 265, rest 0, and so on. So at the end you will get the following bit stream. And then you do the same trick what we did here. So you group always 4 bits, and we get 1 plus 2 plus 8, 11, which is B. 1, 2, 4. And 8. So these are the two possibilities for question 5. Let's go to question number 6. In question number 6, we want to convert the octal number 17253 to a hexadecimal number. So what we do is we need one intermediate step. So we note down the octal number. So the octal number is 1, 7, 2, 5, 3. Octal number, and then we do one intermediate step. This intermediate step is quite simple. We use the binary representation, and with this binary representation we can directly convert to the hexadecimal representation. So the binary representation for this number is 110, because it's just this block of 3. So then we have 5, which is 1, 0, 1. So 1 plus 4 is 5. Then we have 2, which is 1, 0, 1. Then we have 7. 7 is 4, plus 2 is 6, plus 1 is 7. So 1, 1, 1. And then we have 1, which is 1, 0, 0. And then we make again our blocks with 4 bits. So we use this 1, 2, 3, 4, this 1, 2, 3, 4, this, and we convert these bit sequences again to the corresponding hexadecimal representation. So 1 plus 2 plus 8 is 11. So 11 is B. Then 2 plus 8 is 10. 10 is A. And then we have here 2 plus 4 plus 8, which is 14, E. And then we have 1. So this is the hex representation of this octal representation. And this is the solution for question number 6. So let's go to question number 7. Which decimal number is given with the number 487 in hex representation? So it's quite simple, because we compare it just to the binary setup. So if we have the binary setup, we always multiply the according position, and we do the same in the hexadecimal style. So let's write the number. So 487 in hex, which means we have here the 16 to the power of 0, the 16 to the power of 1, the 16 to the power of 2, and then we multiply 4 times 16 to the power of 2, 8 times 16 to the power of 1, plus 7 times 16 to the power of 0. And if you do this, it will result in 1159 in decimal representation. This is question number 7. So let's go to question number 8. What are the limits for unsigned int and for integer? You have now two possibilities. You fill all bits with 1. So it means for integer or unsigned integer, you have 4 bytes. 4 bytes are 32 bits. So let's note we have 32 bits due to 4 bytes, which is used for int or for unsigned int. So the important thing now is u. So int is signed, so you have plus and minus range. The u unsigned is unsigned, so you have just the plus range. So if you have the plus range, then, so if you go to unsigned integer, if you have just the plus range, you start from 0 and go to the maximum. And the maximum is completely filled. And completely filled means you have 2 to the power of 32, which is the next bit of the fifth byte, because it starts with 2 to the power of 0. So the first position is 2 to the power of 0. The last position in 32 bits is 2 to the power of 2 to the power of 31. Therefore, the next position is 2 to the power of 32, which is the first bit of the fifth byte, and you cannot reach it due to you have to subtract from this 1 to get the previous number, which can be reached completely with 4 bytes. So you subtract 1, and this is the maximum number for integer, which is in written way 42949 6 7 2 9 5. So with unsigned integer, you have a maximum number which you can represent of this in decimal. And you start from 0. So it means you have 1 1 1 1 1 1 1 1, the first byte, second byte, third byte, and fourth byte. So again, for the explanation, this is 2 to the power of 0, this is 2 to the power of 31, and here will be 2 to the power of 32. So at this position, so this number is this minus 1. So if we want to represent int, we have to represent the plus and the minus. So therefore we have to spend 1 bit for the sign. And therefore, at least we will have just 7 bits to represent a sign. So it means the maximum and the minimum for this is calculated with 1 bit less. So we have 2 to the power of 31 here, which would be represented here. And therefore, the int range is in the positive part from 0 to 2 to the power of 01 minus 1, which is the max value. So we have 1 bit less. Therefore, we have 2, 1, 4, 7, 4, 8, 3, 6, 4, 7. And to the minus range, we have the same number of bits, but we don't have to represent the 0. Therefore, we have 1 number more available. So we have 2 to the power of 01 minus 1. In the minus range, minus 1. So which is minus 2, 1, 4, 7, 4, 8, 3, 6, 4, 8. So this is the maximum and the minimum number which we can represent in integer values from 0 to this, in unsigned integer value, from 0 to this, in integer values from minus to this. So let's go to question number, what is it? 9. Question number 9. Unix systems define the epoch as starting time of their time counter. And it starts on the 1st of January 1970, 0 o'clock, 0 minutes, 0 seconds. The counter counts seconds beginning on the start date. The internal type time t is defined as long int. On which date does the time counting end on a 32-bit system? So you remember this long int on a 32-bit system is 4 bytes. So we have exactly what we calculated at the moment. So we have 4 bytes, and with these 4 bytes we will end up at the maximum, and this is the maximum of seconds which can be counted, and this will result in a millennium bug. What would happen if we change the type to unsigned long int? And why is the problem maybe automatically solved for our lifetime on a 64-bit system if you just change from 32-bit to 64-bit system without changing anything. You can do the calculations with Excel or MATLAB. I will give you just a solution way what we should do. So we'll see. So what we need is these numbers here. So this is the maximum number of seconds which we can represent. So, and what we now use is we take the 1st of January 1970, 0 o'clock, and add this number as maximum seconds. And if you convert it to this time string, you will see that it will end up on 19th of January 2038. So at this date we will have a flow over, so the carryover will happen and it will jump back to 0, 0, 0, 0, 0, 0, which is then the original time again. So at this date and this time, which will be maybe in our lifetime, so hopefully, you will see that the time will jump back to the original starting time. So if we change this to unsigned long, then we take this again plus this here, which is the max of seconds which we can represent, and then you will end up on 106, 6 o'clock, 28, 15. So we'll get a lot of more time. The problem is that it will end again in next time periods, and therefore if you change to a 64-bit system, then you would have 2 to the power of 64, in our case -1. So we'll have much more bits available, and you shift this into a region which is far away or far out of our normal lifetime. So therefore a change to a 64-bit system from a 32-bit system is quite important. So this is the solution for question 8 and also the solution for question 9. So let's go to question number 10. Question number 10 and 11 deals with color codes, where hexadecimal colors are often used, or where colors are represented with 3 times 8 bits. So for red, green and blue, and therefore we can play a little bit with these numbers. So colors are defined with primary colors RGB, red, green, blue, where each primary color is given by a code from 0 to 255, telling the intensity of the primary color. How many colors can be represented with an RGB? So if we do this, we just have to multiply the maximum number of possibilities which 8-bit number can represent. So this is 2 to the power of 8 for the first byte times 2 to the power of 8 for the second and 2 to the power of 8 for the third. So we have 256 times 256 times 256 different numbers, which result in 16 million possibilities, and this is more than what a human can detect. So therefore the RGB colors are enough for the true color representation for a human view. So this is question number 10. These colors are used in web pages for the color coding, and therefore the next questions deal with this. So we want to change this color code so that we will have another color of the text. Therefore, you find here a nice web page which I will open. So for example, here you can select the color you want to represent. So let's say we want the color 162, here 195, and here 247. Then you will get this color, and then you have these numbers. So you can now directly use this instead of the color code here, but we want to use our knowledge about the hexadecimal system. So we want to convert these numbers to hexadecimal. So I shift it to here and we'll do the conversion. So we have 162, we have 195, and we have 247. So if we convert this to a hexadecimal representation, the red part will be A2, the green part will be C3, and the blue part will be F7. So we will result in this number A2, C3, F7. And if we change the web page in this style so that we enter it here, then we can open this web page and we'll see the color here. So we have now the color, which is exactly this color in the web page. So this is question number 11. Let's go to question number 12. So question number 12 deals with MATLAB and colors. So MATLAB also offers individual colors based on red, green, blue colors. You should draw a circle and paint it with the same color like in question 11. Take care that MATLAB works with floating point red, green, blue maps or colors. So let's open MATLAB. So if we have MATLAB here, we can represent a circle with the function rectangle. So first of all, I want to set a position. Let's say 2, 4, 2, 2. And then we paint a rectangle at this position. With a curvature 1, 1. And with this face color, where we now have to deal with these floating point numbers, but we can easily calculate a floating point number. So if you remember, we had 162. So we now divide 162 by the maximum number of representations. Then we have 195 divided by the maximum number of representations. And then we have 247 and divided by the maximum number of representations. And then we make the axis equal. So what we got now is this. And now we just make the axis equal so that we get a nice rectangle. And you see, it's the same color than what we had here. So this was the solution of question 12. So the next question starts with the Horner scheme or Horner method. The Horner method is used to reduce the operations to convert a binary number to a decimal number. And uses the principle of factoring out of a polynomial function. So for example, if you have the polynomial function a2 times x to the power of 2 or squared plus a1 times x plus a0, then you can write it like this: a2 times x plus a1 times x plus a0, and then you can factor out the x, which means a2 times x plus a1 in parentheses and then times x plus a 0. What does it mean? In this case, you have 1, 2, 3, 4, 5 operations with different requirements, and here you have 1, 2, 3, 4 operations. So if you have a large number like this or larger numbers, then you can reduce this tremendously. So 1, 0, 1, 0, 1, 1, 1, 1, for example. If you want to use this Horner scheme, then I will show it now directly here on the screen, because it's a lot long stuff to write. So what you do is, I shift it a little bit up. So what you do is you write this binary number. So the binary number is this: 1, 1, 1, 1, 0, 1, 0, 1. And then to calculate the decimal number, you would do 1 times 2 to the power of 0, 1 plus 1 times 2 to the power of 1, plus 1 times 2 to the power of 2, and so on. So it would look in operations like this: 1 times 2 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 plus 0, and so on. So if you do the complete operations also with the zeros, so of course you can kick these 0 terms out, but to show you the complete setup, you would have 35 operations. So I don't split between plus and multiplication here, so it's just the number of operations. And then if you start with a factoring out, so you can factor out here the first two, so that at each higher term you will get 1, 2 multiplication less. then you will have just 29, and then if you do it again, you get 24 operations, and so on, so that if you do the complete factoring out, it looks like this. So that you have 1 times 2 multiplied by 2 plus 1, and so on, always with parentheses, so that you reduce the complete number of 35 operations to 14 operations. And this is quite helpful because it reduces the number of operations, it reduces the time, and this is a really helpful conversion method. So let's have a look to the last question in this tutorial. So it's the conversion of the C program, which you find in the PDFs for the lesson, and you should convert it to the MATLAB program. I already showed you the program in the lesson, but try to write your own program which does exactly the same. So in question number 14, we want to convert the C program which you find in the slides. Here is the C program, so it should be easy for you to understand it, because even if you have no experience with C, it should be clear what it is doing. So usually C starts with a main program, and then what is important happens here. So you have 3 values where you store the intermediate values, the iterative steps, results of the iterative steps. You have a factor which you can define here, which is always the same, it's not changed. And then you have a while loop. You do 10,000 iterations. You always print the result, and you do the different calculations. These different calculations are always the same equation or the same calculation in a different format. So in each calculation you have always the iteration parameter for this calculation, and the differences are just mathematical differences. So and then you should calculate the different solutions and then plot it or compare it. In MATLAB you can do it like this. So usually you clear and close all, and you clean up your window, your command window. Then you can do the different steps. In this case, I just do 100. You can also do 10,000 if you want. Then you have these 3 different results. You set the results to a starting value. What I do here is I want to reduce the time which is consumed, so therefore I directly define a matrix or a vector with 100 elements, so that I don't have to rearrange the matrix or vector each time a new value is calculated. And I just set at the right position, I just set the individual values. So we have a starting value, and then we calculate the first calculation, we calculate the second calculation, we calculate the third calculation. This dot 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 just means that we continue in the next line. So if you compare this to the original program, it looks quite similar. You do the calculation here, and then you do the plotting. This is a nice thing with MATLAB. You directly get the plot, and if you let it run, then you will see that it does the calculation, and what you will get is this. And here you can do some manipulations and can play a little bit. So for example, we can zoom in here at this factor where it happened, and you see that there are small changes and things like that. So that's the complete stuff. If you have questions, feel free to contact me, and I hope you will have fun doing these programs and doing these things. Hopefully you do it yourself, because you learn most from this work, and we'll see each other for the next lesson or tutorial. See each other.